This is Quinn Burke, and I just wanted to welcome everyone. We're about 5 after the hour right now, so we're going to go ahead and get started. First of all, I'm so glad that so many of you are here and have signed up for this webinar introducing a very important project titled INFACT, including neurodiversity in foundational and applied computational thinking. We have three excellent speakers today. Dr. Jody Asbell-Clark from Turk, who is the lead PI on the project, Dr. David Weintraub from the University of Maryland, and Dr. Suchi Grover from Stanford University, all who have been working on this work with INFACT, but doing work prior, leading up to this INFACT project. So if we can go to the next slide. Let me talk a little bit. I am a senior research scientist over at Digital Promise, and I'm in learning sciences research. And so please keep an eye out for future webinars coming out of learning science research, or LSR as we call it. LSR is focused on the nature of why, what, and how in terms of learning in and around schools. It is research that is really focused not on the theoretical, but on the practical. So I was really pleased looking at the number of participants on this Zoom call right now who are teachers, who are practitioners within the classroom. That's where LSR's focus really is. As we all know, and as you've heard on other webinars, in terms of where we're at and with your own experience in terms of education, we're in unprecedented times. And one of the things that we're really focusing on at LSR right now is this wider question of educational equity, especially now in the time of a pandemic. Our three speakers today are going to talk a lot about computing and computing equity. We hear about computing equity in terms of a diverse number of students in terms of race, gender, and class. Here we're focusing on sort of a new element here, an element that's been with us for quite a long time, but hasn't received, I think, and others think, near enough attention, and that is learners who are neurodiverse. So if we can go to the next slide. In terms of just a little bit about my parent organization, Digital Promise is doing weekly webinars in and around education, digital technology, and educational equity. Some of you know DP already. We operate within the intersection between educators and researchers, as well as developers, and finding the crossroads between these three and making sure that the solutions that get to students have input from all three, as well as a continuous stream of feedback from all three. So at any rate, that is my quick intro. In terms of two things in terms of logistics, please, as speakers go forward, and each speaker is going to go approximately 10 minutes, put questions in the chat, and I and others are going to monitor that chat. And after each of our three speakers, we're going to have a very brief Q&A that's going to be driven by that chat. Second, so you know, this call is going to be recorded so we can share with the wider community, just so you're fully aware. And third, make sure, as we all do, that your microphone is off throughout the duration. Any questions, as I said earlier, can be placed in the chat, and then we'll make sure that they get to the individual speakers as we go forward. But with that, thanks again for being here with us this morning, this afternoon, depending on your time zone. I'm going to now pass it off to Dr. Jody Asbell-Clark to give us an introduction to INFACT and a wider overview of what this term computational thinking means as it relates to INFACT. So Jody.
Thanks, Quinn, and thanks everybody for coming. I'm Jody Asbell-Clark. I'm a researcher at Turk in Cambridge, Mass. And we have a Department of Education, Innovation and Research project that has allowed us to bring together some of the lead developers and researchers in computational thinking in K through 12 to think together about how to broaden participation, as Quinn said, and particularly towards including neurodiverse students. And by that, it's a general term that I mean people, I'm just going to say, whose brains don't work the way that educators often thought brains worked. It could include kids with autism and dyslexia and ADD, but often it's kids who are under stress or sleepy or just have what we call executive function issues for a wide variety of reasons. So what we're looking at is including a neurodiverse audience in foundational and applied computational thinking. I'm going to go briefly into a definition or what we think of computational thinking, but we could spend the entire webinar on that, and there's many great resources to learn more about it. So I'm going to fly through that and say that CT is a type of problem solving. And what's unique to CT is that it's a systematic type of problem solving. There's a method to the madness. There's a procedure, a way of doing it procedurally. And we're also looking at problem solutions that can be generalizable across contexts, not just solving one specific problem, but a whole type of problems. And therefore, those solutions can be reusable. And sometimes those are referred to as algorithms. Next slide, please. Great. And we focus on several practices of computational thinking. It's a new term, so to say there's a definition it's probably premature to do that. I'm certainly not going to try to define it. But there are practices that most researchers and practitioners are agreeing are fundamental to computational thinking. And this is problem decomposition, breaking down these big unwieldy problems into smaller ones, recognizing patterns and groups of those problems and solutions, abstracting those patterns and generalizing them by removing the specific context and looking at them as more general solutions, and then building algorithms to solve those general types of problems, and also debugging, systematically going through the analysis to find and
You
fix
want me to, what should I write? Because I had no clue.
So, okay, I'll move on. I think, next slide. And we also think of CT not necessarily as a discipline in and of itself, but it transcends disciplines. And we look at applications in coding and robotics, which lead to computer science and other applications, also other forms in science and math. And we've also seen computational thinking play out in ELA, social studies, language development like ELL, and in everyday life. And we think we want to connect that CT across those disciplines for our learners. So my team's been working in CT basically for the past 5 years or more. We have a game, Zumbinis, that Turk made in the early 90s, and I'll show a little example of it later. And we re-released it in 2015. I've been doing research across the country with teachers, mostly in grades 3 through 8, and also within a district and in its entirety. And some of the things we found right away was teachers, especially special ed teachers, came to us and they said, thank you, CT finally gives me the words to do the same types of problem solving I try to teach my kids all the time. I need to have them break down, oops, can we go back just one slide? That they break down the problems into manageable tasks, and they need to see those patterns and generalize their strategies that they learn to deal with daily situations into things, a toolkit that they can have to address life's issues. Okay, next slide, please. The other thing that we heard over and over again was teachers saying, oh my, it's the kids that either have IEPs, individual education plans, or just have been struggling in class. Sometimes they are becoming the leaders in the CT class, and they're excelling at things. And not only are they doing well in school, but they're seeing themselves as smart. Other kids are seeing themselves as smart. sometimes for the first time. And that has such a snowball effect. So we got really interested in this intersection between neurodiversity and CT. And we went back to the research. We saw the assets that are associated: systematic thinking, pattern recognition, as well as related things like idea generation and creativity and perseverance, insistent perseverance. But there's also challenges that are associated with them, having to do with the executive functions, the working memory and cognitive flexibility, self-regulation, and also abstraction, which is really important to CT. So we took these things in mind and are now designing a curriculum and materials, teaching and learning materials, next slide, please, that will provide supports and also sees the cognitive assets of neurodiverse learners in CT. And real quickly, we're providing supports and scaffolds for attention and graphical organizers to help kids keep track of things, representational flexibility, moving from one representation to another, be it English to code or numerals to words, and for numbers, scaffolding that because it's very difficult for some students, helping them make their thinking visible. They might be figuring out a problem, but turning that into a generalizable rule is hard. So we're giving them tools for that, along with motivation and motivation to keep people persistent. And we have the methods of what we call educational data mining, the back-end analytics, just like what Facebook can use to decide what people want and should get, that we can use analytics and algorithms to decide what, based on student behavior, how should we give those scaffolds and when. Next slide, please. So just a quick example of this, and then I'm going to turn it over to my colleagues to explain how this fits more into CT. This is the game Zumbinis that I was talking about. It's a popular learning game, and you can get more information at the URL on the slide. The point of Zumbinis has 12 puzzles, 4 different levels of each puzzle, and they change every time you play. So it's an infinitely unending game. And the puzzles are all based on some form of computational thinking. In this case, you want to get your Zumbinis across the bridges, but each bridge is allergic to certain attributes or values of the attributes of the Zumbinis. So you need to do some systematic testing to figure it out before the bridges fall, and you only have 6 chances to do so in this puzzle. So next slide, please. What we do, oh, excuse me, I'm sorry, could you go back? I didn't point out. It's hard not controlling your own slides. We put up a table to help kids do some bookkeeping. We found that many of the kids could solve the problems, but they lost track of how many Zumbinis they had with each attribute, particularly kids with executive function issues. So we're designing, and these are prototypes. They're going to look much prettier later, but we're designing tools where you could select, oh, I want to test all the Zumbinis with the little helicopter feet, and it'll highlight those for you so you know whether you've used them all or not. It's just a simple bookkeeping tool, does not give the answer, does not even help with the actual CT problem solving, but it gives you a little help on the working memory that you might need. Next slide, please. Similarly, once you've solved the problem, you might have figured it out in your head, but we want you to be more explicit. And this gives you, the tool down to the right, gives you a chance, again, ugly, will be prettier in a full version. It gives you a chance to say, oh, I see, the rule is if the Zumbinis had the one eye, then they went over the bottom bridge. Otherwise, else they went over the top bridge. And it's that explicit language in what we call conditional thinking that's going to be useful for them in future CT projects. So with that, I know it was really quick, sorry, but I had tried to get it in 10 minutes. I'm going to, David and Shushi will be showing you some more applications of how we're pulling this all together. And again, I just want to remind people it's a design research project right now, where we just finished our first year of pulling these things together. We're looking for help in making this the most usable, practical project you can use in your classes. We know that the CT is there, but we also know it takes a lot of work to make this really usable in lots of different situations. And for that, we need your help.
And Jody, this is Quinn. Thanks so much. And I think this gives a really good overview. I got a question, Jody, that shot in here. And before we get to Dave, I just wanted to kind of give you an opportunity. On slide 8, you talk about elements like decomposition, breaking things down, recognizing patterns, using and applying algorithms, you know, and then debugging things. There was a question that came in. It came into me individually, but it said, is there a sequence here that in fact recognizes saying, hey, you start here and then you're supposed to end up here? Or is this more widely something that we're kind of trying to figure out together?
Really good question. We started 5 years ago with what we called a CT progression, and we thought it went problem decomposition, pattern recognition, abstraction, algorithm design. And we've seen that broken so many times that it's very iterative and looping. So we've really moved away from any kind of linear progression. And good thing, because we've been trying to come up with an acronym for them. And Dave Weintraub introduced PRADA, which is a really easy way of saying it, but it goes in all different orders. That's pattern recognition, abstraction, decomposition, algorithm. So yeah, I think it's very iterative and very overlapping. We've also tried to assess these as individual practices, and we can assess all of computational thinking pretty validly or rigorously. To break it down is still quite hard because there's so much overlap. Thanks.
And then Jody, I just wanted to give you one more question. And this was actually on my end, sort of a question that I think probably others are wondering though too. What is the targeted grade range and age of children that this is focusing on?
We're funded to do work in grades 3 through 8. So that's the target age. We also know, because of the neurodiversity, that could expand in either direction. But we are funded to do research in grades 3 through 8.
Great. Well, I want to encourage everyone to please keep questions coming, and those that we don't get to in real time on the line, we certainly are going to follow up. Carly put a note in there too. All these slides are going to get shared with everybody on the call later in a follow-up email. But Jody, thanks so much. And let's pass it over to Dr. David Weintraub.
Great. Thanks, Quinn. Thanks, Jody. So my name is David Weintraub. I'm an assistant professor at the University of Maryland. And I'm going to present some of the motivation and thinking behind alongside the activities we've designed for this project, particularly thinking about ways to introduce neurodiverse learners grades 3 through 8 to computational thinking in unplugged ways. And this is work I'm doing alongside my collaborator, Janet Walko. We have 2 students working with us, Janet B., Margaret Walton. And then we're also doing this in collaboration with the District of Columbia Public Schools. And so Madison Cancer is our lead collaborator there. But important to mention because we have the voices and priorities of teachers and district administrators informing the work that we're doing. And so the big idea we're trying to convey comes across in that, oh, not yet. Go back one, please. Is that, thank you. The infographic that we have in the, or not infographic, the graphic we have in the middle of the screen, this idea of crawl, walk, roll. And so we're thinking a lot about what do crawl and walk look like in terms of introducing to learners to computational thinking before we drop them into full-fledged robotics or programming environments. And the approach that we're taking to get there, we're kind of thinking along 2 different dimensions of how we can design those crawl and walk experiences for learners. Okay, next slide, please. So the first thing that we're thinking about is thinking through multiple ways to support learners in expressing and engaging with computational thinking beyond kind of the conventional programming approach. And so in particular for our project, we're thinking about ways we can have learners gesturing and moving as ways to express and engage computational thinking, using drawing and writing as pathways into engaging in computational thinking, and finally speaking as a way to have learners kind of develop and employ some of these foundational computational thinking skills. And it's particularly important thinking about the population that we're working with, that we provide these multiple ways to engage with computational thinking that can potentially be customized and tailored to the needs and strengths of the learners that we're working with. So these multiple ways to express computational thinking is one pathway. And if you can hop to the next slide, please. Thank you. And then the second way that we're thinking about designing activities to introduce learners to computational thinking is through situating these computational thinking experiences in different contexts. So the context that we've developed activities for so far include science, art, dance, sports, and music. And the idea here is situating the computational thinking in these different themes allows learners with different kind of prior experiences, different sets of knowledge, and different interests, ways to kind of draw on those resources as they're being introduced with and engaging with computational thinking. And then across all of these different activities, there's one more dimension, thank you, that the way we structured each of these activities is they begin in these unplugged contexts where they're moving or speaking or drawing as ways to engage with computational thinking. But then each of these activities ultimately, if the teacher wants, can transition into a more conventional plugged context. So the idea here is they spend some time doing unplugged activities, and then the final step of the unplugged activity will transition them into something like Scratch or Sphero. Thinking about crossing that bridge from unplugged to plugged, at least within these activities. Okay, next slide, please. So having laid out this kind of big picture vision of the activities we're trying to design, I want to quickly run through 3 activities we've developed to try and provide a more concrete sense of what it looks like to kind of integrate these different ideas and priorities. So the first one I want to share is called Mars Rover. It's situated in a science context and particularly focused on algorithm design and uses speaking and moving as the way for kids to engage with computational thinking. Now, this activity might be familiar to a lot of you. This is kind of the conventional playing robot or playing turtle activity. So here the framing is there's a rover on Mars that we're trying to control as it navigates its Mars landscape, collecting rocks for future tests. And so it involves 2 people. It could be 2 learners. It could be a teacher and a learner or an aide and a learner. And so on the right, you can see the setup. It's just some tape on the ground to represent kind of like a home base, and then 3 little, in this case, they're Lego blocks, but 3 objects spread around the room that we're going to try and collect. In this case, those pictures come from Janet B doing it with her son. So we have one person standing in that home base area and a second person who's going to be playing robot or playing rover, and a second person who's giving instructions. And the first phase of the activity is for the person who's giving instructions to kind of give real-time instructions, essentially tell the robot what to do as they're doing it. So this might mean move forward, stop, turn right, bend over, pick this up. And the robot is kind of being pedantic and playing robot like they're supposed to, but is also responding in real time to the information that they're getting. And so then their instructions are given for the robot. Oh, not yet. Instructions are given for the robot to go through and collect these 3 different objects. The second phase we call real-time constrained rover communication. The idea here is acknowledging that robots can't understand all words that humans use. So the person who's giving the instructions and the robot together work out a set of vocabulary that they understand. So instead of the person who's doing the programming being able to say, move forward, okay, go just a little bit forward, yeah, one more step, okay, now stop, which involved a lot of different commands, they would together think through what's a basic set of commands that we can use, like forward, turn, stop, pick up, maybe numbers, to kind of constrain the way that you're giving instructions to the rover. The third phase we call predefined constrained communication. Essentially, now that we have the experience of giving instructions to a robot, we've constrained it to a vocabulary. This next phase is kind of built on the idea that the rover is on Mars, which is really far away, so it takes a long time for instructions to get there. So instead of giving it instructions one at a time, we kind of want to give the robot all the instructions at once for it to carry out. And so here, the person giving the programmer person giving instructions can either write out their set of instructions or kind of verbally recite all the steps that they want the robot to take for the robot to follow. And in this last phase, we can see us really shifting toward developing algorithms where we've developed a way to build a set of a vocabulary, a set of commands that are understood. We have a particular problem, and now we're putting together the steps for the robot to carry out in kind of a conventional algorithmic form. And then the extension for this is for learners to kind of replace the person playing robot with an actual physical robot, a Sphero, Lego Mindstorms, or something like that. So that's one example of an activity. So next slide, please. So a second activity we call picture programming. So this is situated in an art context, primarily focused on debugging, but again, there's going to be aspects of algorithm development, things like that, and is having learners draw on kind of art writing and drawing practices. So the procedure here is learners are going to work in pairs. Each person in the pair is given a simple drawing. So on the right side, you can see 2 examples of drawings. And what they're going to do is, the goal is for them to write out a set of instructions for their partner to recreate the picture that they've been given, but their partner can't actually see the picture. So for example, if I was given the image on the top right, I might write out instructions that say like, draw a triangle, draw a line from the triangle down, and then a line across, and then a line up, and then draw a circle or something like that. And then I would give my partner that set of instructions, and then my partner, following those instructions, would try and recreate the drawing. So that's the initial phase. And then what we do is the person who does the drawing will then give it back to the person who wrote the instructions. And then the person who wrote the instructions can compare what their partner drew to the drawing that they're trying to get them to draw, and then revise their instructions based on differences between the two, which acts as a sort of debugging exercise where we know that there's a target drawing, we can see where the program is, or where the program is leading people, and then they can iteratively revise and improve those instructions as a means to kind of iterate and have a sense of what it's like to identify bugs and revise bugs and get information as you're going. And then so that's a second one. There's a few more phases, but looking at the time, I want to hop to the third and final activity I want to share. This is called Baby Shark Repeat 6 Do. I kind of assume everyone here, whether they want to or not, has heard and is familiar with the Baby Shark song. So here we're using music as a context to explore computational thinking, focusing on the practice of pattern recognition and using kind of writing as the way that learners would express computational thinking ideas. And the high level idea here is that if you look at the structure of the Baby Shark song, there's all sorts of repeating patterns throughout. And so the activity is going to scaffold learners through identifying where repetition happens within the song, and then explore new ways to represent the song in more concise expressions and kind of more modular ways, as a way to kind of re-represent the song, and kind of like a scaffolded way for them to go through what starts at the top right of all the do-do-dos written out to kind of this more modular, like this repeating structure of what a verse is, and you kind of pass in the baby shark verse, the mommy shark verse, the daddy shark verse. And then there's a plugin that can take you to environments like Scratch or Sphero, where there's actually, you can have the robots sing. And with that, that's a sense of the types of unplugged to plugged activities that we're designing. There's a handful more activities, a handful more of ways of engaging, but I'll leave it there. And with that, open to questions before passing it off to Shuchi.
Dave, this is Quinn, and I think this is really interesting. A question just came in from Linda Carmona Bell, and she talks about, she's looking at the 2 different activities you shared and asking a question about gaming and levels, and the notion that each level gets iteratively more difficult, but in a reasonable manner, but allows students, children, to be able to repeat the same skills learn processes that they established on the previous level, but just sort of fine tune them, accentuate them, improve them moving forward. So, in terms of putting kind of a question on this, what are your thoughts just in general about this notion of leveling, and to what extent has, I know you share these sort of phases, do these phases sort of translate to that notion of levels? I hope that makes sense.
Yeah, that does make sense, and thank you for the question. We've been thinking about it less from like levels gamification perspective, and more from a kind of like incremental development of skills. There's certainly parallels between the two, but our design approach has been much more thinking about, and this gets back to this idea of kind of pathways into computational thinking. What are ways that what are kind of like the most accessible, intuitive, kind of lowest threshold pathways into learners engaging with these authentic computational thinking practices, and then how can we layer on new ideas that will move them towards what we think are these kind of on-ramps to the type of computational thinking learning that we're going to hear about next from Shuchi, and that kind of like unplug to plug pathway, layering in these new ideas. But certainly parallels there. And we could also think about, as a teacher, kind of knowing your students, like if that's something that might be really exciting or engaging or motivating to them, it wouldn't be that difficult to kind of make that twist in framing.
And Dave, one more question before we pass to Suchi. This one came from Latora Cabrera just a minute ago. Teachers like this stuff. I think they find it valuable. Sometimes it's really hard, and I think this has come up in conversations within the group too. How do you make sure that this is something that can be incorporated? You know, I think you've talked about this, but in terms of sort of unplugged activities, you know, what's your experience with teachers trying to work some of this into a math class, a science class, versus sort of a standalone activity that we're going to do on a slow Friday when it's a half day? You know, is that something that you've seen some success with teachers?
Yeah, so we've definitely had success with the kind of embedded computational thinking approach, where we can kind of situate particular mathematical ideas, say, that could fit within a math classroom. The experience we've had with these specific in-fact activities, like the ones I've shared and others that we've developed for this project, we've been working with special ed teachers who have a bit more flexibility in terms of how and when they roll out activities. And so it's been, the feedback we've gotten from the teachers for the in-fact materials has been less directly concerned with alignment to, say, standards or like content coverage, and much more about tweaks to be made to help support learners in terms of engagement, or like tweaks that we've made or things that might be too big of a jump or too abstract, that type of feedback in terms of supporting students in these special ed classrooms. That's the feedback we've gotten from this. But yeah, point well taken about the importance of kind of figuring out teachers' needs and aligning your materials to kind of match them in the classroom constraints.
Okay, great. Well, Dave, thanks so much.
Yeah.
We will now head over to our third and final speaker for today, Suchi Grover.
Hi, everyone. I'm Shuchi. I am a senior research scientist at Looking Glass Ventures, a small R&D venture out on the West Coast in Palo Alto, also a visiting scholar at Stanford University. So building on that wonderful foundation to CT that Jody and David provided, I'm going to talk about how we bring attention to data and data abstraction along with computational, along with algorithmic thinking in fact. Next slide, please. So data, as we all know, is everywhere and increasingly so. And often data is pretty central in CT applied settings. Data is often the linchpin for integrating computational thinking in various subjects, where data from the domain sort of is what is being analyzed and used in the process of problem solving or understanding phenomena or whatever, modeling. So, you know, it's a great way to sort of integrate in any kind of subject when you are sort of centering on data often. Next slide, please. So part of the foundational learning of CT, students must understand and appreciate data abstraction and creating generalizable solutions, as Jody said, and that data can be of various types. Students often deal only with numeric data in mathematics or science class, but in real life, data can be of any kind, and that's where CT sort of helps them appreciate that. They can encounter different kinds of numeric, character, string, Boolean, all those kinds of data, and they have to understand how such data is represented and manipulated. Next slide, please. So for example, in applied settings, when students have to apply CT in a modeling or simulation setting in a science or social studies classroom, they work with various parameters that control the model or are relevant to the model or to the basically to the scientific or social phenomena that they're studying. And these parameters could be, as you can see in that model, on or off, which is like a Boolean flag, or numbers, percentages. The numbers have various ranges and such. Click again. Similarly, when children work in any number of instances, when they're programming in Scratch or whatever, they have name, age, weight, height, different kinds of variables and data that they're using, even in their simplest programs, game, the score of the game, counters and such. And click again, even when they work with strings, for example, and data structures in maybe a language arts classroom where they're sort of working thinking about rules of grammar for language arts. So Yeah, so one of the fundamental understandings in algorithmic design is this idea of the variable as a way of abstracting or representing data in a program. So we, in fact, are helping children understand that a variable is basically a named quantity that can take on different values over time, that variables can be changed or manipulated through operators and expressions, in addition to arithmetic operators that they use. In mathematics, they come to appreciate the use of relational. Well, they do a little bit of relational in math too, but not the is equal often or not equal, Boolean, string, and other operators. Next slide, please. And for this, we've adapted activities from my past work that have involved designing unplugged and digital activities that focus on these ideas. And they've also been tested in classrooms. So we bring some of that feedback into adapting and sort of building on those activities. Next slide. So among the various forms of that these activities take, we have unplugged activities, just like David showed, there's this sort of progression. So in their foundational learning, they often sort of wrestle with these ideas in unplugged contexts, often drawn from everyday scenarios, whether it's, you know, daily temperature or weather charts, game scores, cost of goods, size of clothing, and they can create their own expressions when they've sort of understood how to use, you know, what Boolean operators mean or whatever. They can create their own expressions, again, from everyday scenarios. Next slide, please. And we also have unplugged game-like activities that help children get an introduction to conditional logic through evaluating expressions. Could you click, please? Through evaluating expressions that involve numbers and arithmetic and relational expressions. Great connections to mathematics, as you can see. Click again, please. These expressions could even involve Boolean expressions. And this activity we found is very generative in that a student can play it alone or in pairs, at home, online, offline, with you know, with an adult or with a peer. And so, you know, given the current times, we've sort of built in the flexibility to use this activity in various ways. And it's very extensible too. Students can create their own rules, teachers can create more rules and such. It can be played with any number of die. You know, the more die you have, the more flexibility you have in the rules that you create, etc. Dice, sorry. If you go back yes, no, this is fine. And so I just wanted to show that these are part of those foundational understandings that we're trying to build before students use them in applied settings. The next one, next slide, please. So like the Zumbinis game, you know, another part of foundational learning is to engage in these digital interactives and game-like non-programming activities that we've designed that introduce kids to operators and expressions of various kinds. Click, please. So following these foundational activities, students transition, as David had described, into something like a Sphero activity or you know, a Scratch activity. And here, you know, again, given that it's grades 3 to 8, we have a gentle introduction in the beginning where they encounter these same ideas in a Scratch programming environment. They work with variables, things that change. They work with basic conditional logic. And like Jody had described, we are basically incorporating EF scaffolds, graphic organizers to help children that may need those kind of supports. And again, so these are the applied activities that students do. And click, please. All of this is to basically help build their understanding toward using data abstraction in mathematics, in science, in social studies, modeling. All of this requires this fundamental understanding of data abstraction and how it basically intertwines with algorithm design, conditional logic, and loops and such. And so those are the kinds of understandings that we're building through these set of activities. That's it from me.
Great. Well, I'm going to get to the questions in a second here, but thanks, Suchi. Jody mentioned this at the outset, but I think it's really important to restate here. If anybody is interested in learning more about this, and I'm going to pass it to Jody in just a second to talk a little bit more about this generally, we really encourage you to fill out this participant survey. Anything that's shared here, who are the students you are working with? Do you have colleagues who are working with students who are neurodiverse? Have you done computational activities with your students, maker activities with your students? Do some of these sequences, these approaches resonate with you? That's all stuff that we really are very interested in learning about. Jody, let me throw it to you for a minute. And then I think there's two questions we can bounce back. And I know we want to end early enough that everyone can go off to the next meeting they have. But Jody, if you just want to kind of put together a little bit more of a holistic picture, that'd be great.
Sure. Well, just about the design research. So as you see, we have tons of pieces, we have stuff, but we're still kind of figuring out the best ways to stitch it together and how to, I'm going to say package, but what I mean is put things together in a way that's implementable in the classroom. We have our ideas, but we want input on that. And then we're also doing research where we're figuring out where to put these scaffolds, but we need to observe, I'm going to use that word in air quotes for, we don't know what that exactly means these days, but to observe how a wide variety of students use or don't use these types of supports. And that's going to help us make a better product. So to do that, when we wrote the proposal, we said, oh, we'll go out and we're going to find 40 classes and it's going to look like this. And we're going to go in. And of course, everything's changed. And we took that as a challenge and said, okay, so how can we be best, not only in research, but of service right now? So what we're really thinking is, who are the educators out there who have kids who want to work on this and are free floating and may not have the situation, their classroom or support or whatever it is that would help them? We will help you. We're going to put a team member with every participating teacher to what we call a buddy, to make sure that we can step people through what they need to get this to work in their classroom and hopefully learn from them how to make it better. So that's what we're looking for this year. Next year, we're going to send it out as a field test, but for this year, we're really looking for those one-on-one design partners. And you could be a homeschooler, learning pod, parent, classroom teacher, whatever situation has kids who need this kind of stuff.
And Jody, I'm going to follow up just on your point. In terms of, Marion Casey just made a point, she made a point about students versus all students, which I think is worthwhile. So there's a question here of, hey, are we just looking for children who are neurodiverse in grades 3 through 8? Are we looking for a wider cut with students? So that's one consideration. But then more widely, I think, Marion, I'm going to go back to a question you posted there earlier. There's always a lot of metaphors for programming. Some people see it as sort of a grounded form of mathematics. Some feel it's best kind of conceived as sort of a maker project type of approach. Others see it as sort of learning a language, which is more akin to the coding piece. I think there's a more immediate questions Marion's asking about, hey, is this all students or just children who are neurodiverse? But then this more second question, which I think Suchi and Dave may want to weigh in. Is there an ideal metaphor for how programming should be approached with children of these ages? So I guess in some sense,
I'll hit
really,
the
I'll go to
first one.
you.
I'll leave the second one to David Suchi. So first of all, I mean, the irony is, of course, neurodiverse means the whole spectrum. So yes, we want all kids. We will make sure that our overall target audience has enough kids with either diagnosed or undiagnosed EF challenges that we're getting the data that we need to make sure that it's working with them, but we also want to include other students. So don't let that be your filter. If you think you have kids that want to use it, go ahead and sign up. We'll make sure we get enough neurodiverse kids in our sample to do our research.
And I just want to add to another point that was asked earlier about grade levels and whether we foreground certain, or if there's a sequence in the way we introduce these concepts. And I just want to add to what Jody had said, that we see all of this as a spiral, from grades 3 to 8. And given that we're looking at differentiation and neurodiversity, we have made a conscious effort not to target a certain activity as this is grade 3, or this is grade 5, or this is grade 8. We target it as a spectrum of easy, medium, difficult, or something like that. The point being that a child in grade 5 could use a grade 3 activity or a grade 8 activity, depending on where they're at in their learning and what kinds of supports they need. And so all of this is sort of, it's sort of a spiral. And of course, we do recognize that certain things will be more relevant for the middle school, just given where children are at in grade 3 versus grade 8. There's, of course, that appreciation. Okay, metaphor. Does Dave want to take that question, or shall I give my view?
I'm happy to. So I'll give my view, Shuchi, and you can decide if yours is more helpful. Because my answer is not going to be that helpful, in that I don't think there's one universal metaphor that works best for everyone, but instead is much more tailored to the particular context of what the learning experience is going to be, the particular background, interest, and prior experiences of the learner. So it's much more like in the hands of an expert teacher who kind of knows the best way to help a learner kind of understand what programming is based on their own experiences and the particularities of the context that they're in. So sorry, that's not a very helpful answer, but that's how I think about it.
I'll just add to that. I like that answer, and I think it is how we have viewed this. But we also see some of this sort of going into STEM classrooms, math and science classrooms, some of these activities. And there, I think the framing of programming can be very much, a tool to sort of analyze something, think of a generalized solution, generalizable solution, do things that they may not have been able to do if they weren't using programming. And so I think there is this idea that you can apply the CT that you have learned in unplugged settings in a game or whatever, your conditional logic, your understanding of problem decomposition or whatever, and now bring it with this tool, this programming environment, and let's see what we can do with this to analyze whatever it is that we want to study and analyze.
And I just want to go back and say that if you think of CT as a type of problem solving, then it's a method of, it's a way of thinking about problems and way of approaching problems that can be applied to anything, and including daily life. So.
Well, I think Susan Jones put a nice comment in here. It's helpful these days to be able just to say, I am not neurotypical. I certainly am not myself. But Jody, I have one more question. I know we're getting to 9:55 on the, out here in California, so we're going to let people go. But I'm a teacher. I'm interested in doing a little bit more. I do have students who are neurodiverse. I have done some making activities. If I sign up in terms of next steps, can you just give us a ballpark? Because in fact, it's at the early stages right now in a multi-year grant. So, but Jody, I thought you could kind of maybe just fill in some broad strokes.
So ideally what would happen is you sign up, you get hooked up with one of us, we find out what your teaching situation needs are, and we send you a bunch of materials, and you fly off and you love them, and we tell you, and you meet with us and tell us what worked and what didn't work and what we'd like to change. That's the ideal. The one little hiccup on that is something called IRB, Institutional Review Boards, or human subject. For us to work with your kids, we have to jump through some hoops and get some consent for good reason. I'm not belittling that, to protect you. And so we are set to do that, but how much time that takes often depends on the situation on your end. So I can't promise timing, but I can say that we will work. You fill out the form that the link's been going around, and we will get back to you very quickly to find out what your situation is and start that process quickly and get to you as soon as we can. And I would say that we are collecting for this design one-on-one research for this year, but for next year, if all goes as planned, we need 960 students to study. So we're going to be being even more, recruiting much more widely next year or this year for next year to do a full study. And one more thing is what a full study entails is probably using these materials about 10 hours or more in the setting. And then doing the pre and post test and some survey stuff around that. So does that answer a question?
That's, I think, really helpful. Listen, I know we're at the top of the hour, getting very close. So I just want to thank our three speakers. I want to thank Carly Chilman and Corinne Colgan for all their support putting this together. And I want to thank all of you for joining us today. I think there's a lot here, and I really will encourage one more time, please do fill out that participant survey form. We're interested in learning a little bit more about you and your students, your situation. I hope everyone has a fantastic Tuesday and a great rest of the week. Thanks again for joining us today.
Thanks, everyone.